like changing glacial hazards. It's driving things like changing water resource availability, as well as changing things like sea level rise. So what we really want to know is, how is this going to occur in the future? Are things going to accelerate, or are they going to continue at this kind of static level? We have numerical simulations of glacier behavior. These are all models that come from multiple sets of numerical models, and they're run for different climate change futures. And I've picked out Alaska from several of these recent papers. And they all largely show a fairly linear behavior of Alaskan ice over the next 100 years, or next 80 years to the year 2100. Fairly temperature dependent and fairly linear behavior, no matter what climate scenario we're looking at. So we have seen this really great effort to predict future glacier behavior. It's largely based, however, on fairly straightforward models that tend to neglect frontal ablation. So they're neglecting calving, or they're greatly simplifying calving. And they also simplify ice flow by particularly things like lateral stresses. So there's a variation in complexity of these models, but all of them are inherently fairly simple models. More recently, we have the Rouncetal paper that uses a more complex range of models that include some frontal ablation, they include debris cover, and we're still seeing this fairly linear progression over the next 100 years. And I think this is really interesting, because Alaska, Canada, places like this, they're somewhere where we have a lot of fairly low slope glaciers. Juneau Icefield, for example, and many of the other ice fields in Alaska have fairly low slope accumulation centers. These are places where the ice field is fairly, unlike a mountain glacier, the ice field is fairly flat in its upper parts. And this hypsometry, this distribution of area with altitude, can be quite important in modulating how the glaciers are responding to climate change. That's because we have things like increased sensitivity of the surface mass balance to a rise in the annual snow line or equilibrium line altitude. And so we might expect a non-linear response for these ice fields to a linear rise in temperature, or to a stepwise rise in temperature. And ultimately, I think some of these models are not necessarily capturing these non-linear processes, and this increased mass balance sensitivity to that rise in equilibrium altitude. We also have other factors. So, for example, a mountain glacier may be able to retreat or shrink in response to a change in temperature. And then if the temperature stabilizes, that mountain glacier may be able to find a new equilibrium. And that might not be the case for things like mountain glaciers, where a rise in ELA may lead to an unsustainably small accumulation area, or even a lack of snow across all of that plateau accumulation area. This is the hypsometry of all the glaciers in Alaska, all the ice fields in Alaska. So we've got a number of large ice fields in this region. Some of them are very top heavy, others are very bottom heavy, because they have large, low-lying ablation rich tongues. So we have the weighting of that distribution with altitude. We can see that Juneau Icefield, Stickeen Icefield, Sargent, Harding, some of the other ones are very top heavy. But we also have a number that have this kind of low slope accumulation area. So there's a number of ice fields across here with these low slope accumulations areas. So for example, the Brady Icefield, Cluane Icefield, Sargent Icefield also all have that plateau hypsometry. So the focus of this project is Juneau Icefield, and we're specifically looking at how this topography, how this hypsometry might affect glacier behavior in the past, so that we can use that to maybe try and understand how it might affect it in the future. This is Juneau Icefield. It's one of the larger ice fields. I think it's something like 6th largest ice field in the world, and it straddles that US-Canada border. It's mostly terminating on land, but there's one glacier, Taku Glacier, that terminates in this fjord here. In terms of climate, there's been a shift in about 1976. So we had this, you can see this temperature graph here, and we've got precipitation graph down here. And after 1976, there's a clear shift in temperature. That means that temperatures over the last 20 years have been about 1 degree warmer. And these red circles are all the 10 warmest years, and the blue circles are all the 10 blue circles are the 10 coldest years. And this shift in climate was also associated with a decrease in autumn precipitation. And we know that the glacier mass balance is really strongly declining. So we've got Chris McNeil's work here showing this long mass balance record starting since the 1940s for Lemon Creek Glacier, and it's consistently accelerating negative mass balance for Juneau Icefield. So our aim was to understand how the topography might control dynamics and behaviour of the icefield over the last 250 years or so. This is Juneau Icefield itself. That's Taku Glacier, the biggest glacier in the icefield, the biggest glacier in the icefield in the background. And then in the foreground, we've got the camp that the Juneau Icefield Research Programme use. And here are some of our colleagues from that Juneau Icefield Research Programme that are responsible for that really long record of glacier mass balance. And you can see how flat Taku Glacier is. The slope of that glacier never really gets above about 1 degree, and I can attest to the fact that it's very flat, having skied across it, to get hardly any slope to help you at any time. Okay, so we have a number of methods. We first undertook mapping of the glacier structures, and I did this using Sentinel-2 imagery from the year 2019. This is a year with a particularly high snow line, so it's particularly appropriate for glaciologically structural mapping. It was all manually mapped, no automated mapping. We also used Arctic DEM. And you can see that we use the black and white bands because they really pick out the glacier structures more than those composite true colour Sentinel-2 imagery. Our data sets included the Randolph Glacier Imagery version 6, and then archival aerial photographs that were flown in the 1940s and 1970s. We have Landsat imagery, the Arctic DEM and ASTA DMs made by the Hugen et al. 2021 dataset. We also have historical data and published chronological data. We used all of those sources of information to provide time slices of the icefield throughout the last 250 years. So we reconstructed the extent and volume of the ice in AD 1770, and then used structure from motion to create new orthomosaics and digital elevation models in 1948 and 1979. We have Landsat in the 1990s and 2005, and then we have the Hugen et al. Datasets from 2000, 2010 and 2020. So we have a number of time slices of both area and volume. Okay, so we'll start with how the icefield looks today. It's a plateau icefield with over 1,000 glaciers. Most of the glaciers are really, really small, but some of them are really, really big. And this is Taku Glacier again behind us, which is about 700 kilometers squared and basically takes up most of the southeastern portion of the icefield. We created a structural map of the entire icefield, and this was published last summer. So here you can see the icefields. You should be able to see the orange and the pale yellow. That's the interconnected plateau that's very low slope. And then around the edge of the plateau, we've got lots and lots of crevasses, ogives, all sorts of foliation and lineations. So we have this overall glaciological map. We mapped thousands of crevasses, but mostly they're occurring in heavily crevassed zones. This is obviously a minimum estimate because the resolution of the Sentinel imagery doesn't allow us to map every single crevasse, and some may also be snow-covered. We also mapped things like ogives, longitudinal foliations, primary stratification, and so on. If we zoom in, you can see some of the crevasses that have been mapped, and I've pulled out the icefall type crevasses in purple. So here we've got Herbert Glacier and Mendenhall Glacier. You can see that yellow plateau, and then at the edge of the plateau, we have these icefalls. And these icefalls are common all around the edge of the plateau. In fact, we mapped something like 150 icefalls on 55 glaciers, and they are quite altitudinally, narrowly grouped. So there's a histogram of the elevation of those icefalls, and they're all occurring really around the edge of that plateau. This is what these icefalls look like when you're actually standing at them. This is another one of the Juneau Icefield research camps. And this is Gilkey Glacier, standing at the top of the icefall, looking down it, and down at those beautiful ogives just stretching away into the distance. You can see on the longitudinal cross profile how steep that icefall is. So very, very steep ice. You can see how rough it is. It's also kind of darker, it's bluer, and it's very chaotically broken up. One thing that became obvious whilst we were mapping these glaciers and the structures on these glaciers was that in a number of places there's bare rock appearing in the middle of the glacier, and we called these disconnections. Now, there are a couple of places where these have been observed on other glaciers around the world, but mostly this is just anecdotal. So I think this is one of the first attempts to map these systematically across the whole of the ice field. You can see some nice examples here from Denver Glacier, Herbert Glacier, a little Valley Glacier, Eagle Glacier, and Thiel Glacier. And in these places, there is hardly any ice flow that's coming from that cirque accumulation area or the plateau accumulation area down into that glacier tongue. What we think is happening is that at these ice falls, that glacier ice is quite thin. It's thin because the ice surface slope is very steep. It's also very crevassed, and it's darker and it's rougher. All of that means that if you start to get melt occurring at that key point of vulnerability within the middle of the glacier, you more easily expose bare rock within the middle of that glacier. And we can see that happening very clearly in places like Denver Glacier and Eagle Glacier, and these little pink circles are where we've mapped these disconnections. We call them disconnections because there is a disconnect between the accumulation area and the tongue. As a result, the glacier tongues below these disconnections have statistically significantly more debris than on other glaciers. So this is a new phenomenon. Have they been happening a long time? Are they reversible? Is this common on other ice fields? Are all questions that we immediately began asking ourselves. Here's some examples. I don't think the pictures are the best examples, but you can see some examples here of these disconnections. So here you have a glacier tongue with that disconnection occurring, and that bare rock, that ice scoured, newly exposed bare rock now occurring within the middle of it. These aren't the same as reconstituted glaciers, which are common in places like, for example, the Antarctic Peninsula, where you have a very sharp plateau edge and a very, very steep slope. The average surface slope of these ranges is about 30 degrees, 20 to 30 degrees is the mean. So these are they're not a normal part of the glacier. Here we show how the glacier disconnections and the icefall crevasses are occurring within that same elevational band. So we're seeing that there is a coincidence of elevational range between these disconnections and these icefall crevasses. Some nice more examples here of icefall crevasses around the edge of the plateau for Battle Glacier, Herbert Glacier, and Eagle Glacier. So what we argue is happening is that the rise in the equilibrium line altitudes that's being measured at Lemon Creek Glacier and Taku Glacier is starting to intersect increasingly with that elevational range of the icefalls. Here we have the elevational range of the icefalls and the ELAs of two glaciers that have been measured since the 1940s. And this is the elevational range of these disconnections. So as that snow line is rising, we're getting increased melt happening at vulnerable points on the glacier. These areas of steep ice, these areas of thin ice, these areas of very rough ice where we've got perhaps darker, bluer ice being visible. Okay, I want to talk about the glacial geomorphology of Juneau Icefields, and I couldn't resist putting in this pretty picture of Juneau Icefield glacial geomorphology. We've mapped features around the entirety of the icefield. So here we have our overview map published last year and some nice sections that show some of that glacial geomorphology. So we've got things like moraines, trim lines, the pink is areas of ice scoured bedrock. We have morainic kind of drift sediments, and we have roche moutonnées, which are these green lines or streamlined glacial bedrock. If you go to visit some of these moraines in the field, on the top of the ice field, everything is very bare, it's very stripped of vegetation, there's hardly anything growing. And then down at the foot of the glacier, everything is very lush, there's this very rich rainforest vegetation. We have these Sitka spruce and kind of coniferous plants grown on these moraines. They're very bouldery, they're very open framework boulders once you dig away some of the overlying soil and kind of compost. And there's often lots of little kettle lakes in between them as well. So we can see that we've got some nice Piedmont lobe moraines on that lower, flatter valley floor as those glaciers have reached the terminus of the valley and then kind of spread out because they're no longer laterally confined. Some more examples of the moraines around Twin Glacier Lake. And here's my colleague Lindsay Nicholson demonstrating why there's not been so much work on these moraines, because they are very overgrown with alder, particularly in the meltwater channels between the moraine crests. She's only a couple of meters away from me here. You can barely see her. There's no path. You have to hack your way through with a machete. So it's quite hard work working through these moraines, because here you have a very typical swale between the moraines filled with alder, and then you can see the spruce on those moraine crests. And if you want to go from inner moraine to outer moraine, you have to navigate through all this heavy vegetation, which is of course full of bears and mosquitoes and moose and other unfriendly things like that. Okay, so we wanted to reconstruct Juneau Icefield during the Little Ice Age. There hasn't been that much published on the timing of the Little Ice Age. There is some limited historical data for the moraines close to the towns. So we have some archival evidence from the glaciers near the town of Juneau, from Taku, Herbert, Mendenhall and Eagle glaciers. And they all indicate Little Ice Age at 1770 AD. We do know that there were readvances at other times in other parts of the Holocene and other parts of Alaska, but there's scanty evidence for that at Juneau Icefield. And so that's an ongoing project that hopefully we'll have an update for in the near future. We used these fresh moraines, these kind of fresher neoglacial moraines, to reconstruct the glacier extent during the Little Ice Age. So for example, here we have Taku Glacier. These dashed black lines are the mapped extent of the glacier by the US Coast Guard in the past. And there's also this big blue ice dam lake in the Taku Valley, and that's been reported widely in the archival records. Taku Glacier is quite anomalous because Taku Glacier was smaller in 1890 than it is today. It grew smaller because it was receding up a deep channel. It then infilled that channel with lots of sediment, and that cut it off from the marine influence. And so it then started to re-advance again. So here we have Taku Glacier being quite small in 1890, then re-advancing through to the present day. Here we have the reconstructed equilibrium line altitudes and the reconstructed surface elevation that we're using by looking at the heights of those moraine crests and those trim lines from the Little Ice Age. So we have thinning in most places across the ice field. So a small change in the surface elevation of Taku Glacier as it's changed from marine terminating, partially floating fjord glacier to a what it is today, which is essentially terminating in small lagoons. But most of the other glaciers, we have this lots and lots of thinning on those glacier tongues. And these coloured circles here are the reconstructed equilibrium line altitudes, showing that east-west gradient that's likely driven by changes in precipitation over the ice field due to orographic precipitation effects. Okay, so glacier area and volume change from 1770 to 2019 AD. I couldn't resist putting one of Ben Huff's nice pictures here. Here we have our reconstructed ice field area change, and we have reconstructed rates of change over particular periods of time. So we go from minus 3.7 kilometers squared per annum from 1770 to 1948, up to 25 kilometers squared per annum from 2005 to 2015, rising to 38 kilometers squared per annum from 2015 to 2019. So the rate of change is steadily accelerating. Although it's quite a long time between 1770 and 1948, for the small number of glaciers that were surveyed in the 1900s, we're able to say that that rate of change has been fairly steady over that period of time. There's not really much evidence of big dramatic fluctuations. So here we have the red, dark red, it's that little ice age going through to the present day, which is shown in white. This rate of acceleration really accelerates after the year 2005. So it's now 7 times faster than it was from 1948 to 1979. We know that we had the climate shift with the change in the Aleutian Low after 1976, but we're still 5 times faster now than we were from 1979 to 1990. Essentially, this is really accelerated after 2005 following regional warming. We also have the first long-term record of glacier area and volume change, which show 3 distinct periods, consistent rates of thinning from the Little Ice Age to 1979, a rise in the rate from 1979 to 2010, and then a doubling again of that rate after the year 2010. The mean thinning, again, it's showing acceleration after the year 2010. What happened in 2010 was that we started to get thinning across the whole of the plateau. I've put on here the change in elevation per annum. This is blue to red. And I've also put on the disconnections that occurred in the year 2010 to the year 2020, as observed in that archival imagery. And we can see really the thinning is now pervasive across the whole of the plateau, whereas previously there was less thinning on the plateau. We've reached a threshold point by which we have thinning occurring even at those higher elevations. And because we have this low surface slope, we're susceptible to these vulnerabilities. The number of disconnections has accelerated. Here is the mean height with standard deviation of the heights of the disconnections in this top graph, and the coloured circles are the measured equilibrium line altitudes from Lemon Creek Glacier and Taku Glacier. We can see that over the last 10 years, those equilibrium line altitudes have really started to intersect increasingly commonly with those key points of vulnerability on the glacier. And as a result, the number of disconnections is sharply accelerating. Okay, so we can summarize to say that the icefield volume change was about -1 kilometre cubed per annum from 1948 to 1979, rising from 1979 to 2000, and then doubling to almost -6 kilometres cubed per annum from 2010 to 2020. And that this rapidly accelerating recession is being driven by rising air temperatures. These ELAs are now reaching the rim of the plateau despite increasing snowfall. This is driving thinning across the plateau, it's driving increased melt, and it's driving increased glacier disconnections. So we have this strongly non-linear glacier response conditioned by this hypsometry. So I attempted with my absolute best Photoshop skills to sketch out what it might look like and the different processes that are happening, and how we might change this by the year 2100. Here we have our current ELA with our current snow line here. If this ELA rises, this means that we have darker snow and ice and lower albedo. We have perhaps glacier recession, which means that we have darker rocks and increased radiative forcing. This increased radiative forcing encourages disconnections to grow and to become more substantial. We're likely to have glaciers and icefalls thinning and glaciers disconnecting. This increases the fragmentation of our glaciers and accelerates melt by changing the regional albedo. Essentially, we have more darker hill slopes, more darker rocks within the glacier, all of which contribute to radiative forcing and increased glacier melt. We'll have surface lowering of our glaciers, increased crevassing as things become more topographically constrained. This will lower albedo and increases roughness, which can increase the turbulent heat flux. So all of these things together act to as a positive feedback to accelerate glacier melt. I would suggest that we need to consider whether these disconnections are happening in other places across the world. Is this something that's restricted to just glaciers in Alaska, or is this something that is happening in lots and lots of different ice masses and lots of different hypsometries and different kinds of glacier? And I think we have time for a few questions, and I'll just leave with a pretty picture up. Thank you.
Thank you very much, Bethan. That was brilliant. And I really enjoyed all of the pictures. Thank you. So Rita, could you open the chat? Or Luca? Forgot to do that. So the chat will be open at any second for questions. In the meantime, I had one very quick question. Well, I don't know if it's a quick question, but I'm not a glaciologist, so sorry if this is a silly question. But when the glacier disconnects, does that what happens to the bits of ice on either side of the disconnect? Does the upper one flow, or does it just stay put? Or
well, it depends how you define a disconnection, and I defined it as somewhere where the whole of the ice flow unit has been separated from that feeder ice above it. So, for example, there may be ice in other cirques coming down, but that one flow unit has been completely separated or beheaded, perhaps, by that from the glacier ice above. So that's really restricting the amount of flow that's coming through. The ice is essentially stuck up above, and it's not making it down to the trunk. I mean, the response of the glacier to this needs more careful work. We have observed that the glacier tongue rapidly decays, so the amount of thinning that's occurring on these glacier tongues is much faster than it is on glacier tongues that are not disconnected. So there's a statistically significant acceleration in thinning. But the glacier above the disconnection might have less ablation now that you've removed that big ablating glacier tongue, but that becomes a moot point if you're on a very flat area and your ELA is now above the top of your glacier.
Okay, interesting. Okay, I'll go ahead and ask my other question while people are still typing. I was thinking about we have a question. I'll save it. So Sun Hospital asks, is it possible to observe a disconnection event from sea ice satellite data available?
Yeah, I'm not sure I understand the question. Is this like a different sensor on the satellite that you're referring to, as opposed to we were only looking at this with optical satellite imagery, but if you have thermal sensors and things like that, you may well see a change because the rocks are very warm compared to the glacier ice, because they have a lot of radiation absorption, so they warm up a lot during the day. But yeah, I'm sure you could look at using optical satellite imagery to look at these in other places.
I've just added remote sensing. I don't know if that helps. Luca, can I take away?
We have another question. I will have also one for a bit later. But Trevor Faulkner is first thanking you for this great talk and asking how much loss is from melting in supraglacial streams and lakes, ice dam lakes, subglacial reservoirs and lakes, and along the subglacial waterways.
Yeah, there's a paper by, I think it's Young et al. 22, and I can't remember the exact figure, but they're looking at measuring discharge from Juneau Icefield in the rivers and quantifying how much melt there is. We were just looking at the volume change and thinning of the glaciers, but you can also calculate volume loss by looking at how the discharge changes downstream. So I think the Young et al. Paper has the answer to that question.
But do you have a sense from all of your observations, from you being in the field, of the relative importance of these different areas where ice is going to melt on the glacier top?
Yeah, I mean, the ice dam lakes in Juneau are quite interesting. So some of these ice dam lakes, most of these ice dam lakes are emptying every summer anyway. So these ice dam lakes reach flotation quite regularly every summer and then discharge catastrophically as a fairly regular event. And in fact, some of them are called great names like Lake No Lake, which I think is a wonderful name for a lake. Sometimes there's a lake and sometimes there's no lake. So it's very descriptive. So these glacier lakes are an important part of the system, but they're also quite a regular part of the system. Most of the volume loss is then being discharged through subglacial channels. We didn't see that much superglacial discharge on the satellite imagery. I think there's also quite large fern aquifers, which are then percolating down through and coming down. I think some of the people in this field, in this room, Zoom room, might have probed some of these or even tested how big these fern aquifers are.
Okay, thank you so much, Bethan. We have another question from Ben, who's asking if at the disconnections, is subglacial water flow exposed, and does this influence melting downstream?
I think they're fairly steep slopes. So any water, they're on about kind of 20 to 30 degree slopes. So any water is washed away downstream fairly quickly. So I think if there is any melt, that's quite quickly evacuated. On the Sentinel imagery, because the resolution is about 10 meters, you don't necessarily see small amounts of water. And we didn't see any standing water around these. The standing water is in the kind of very low slope areas.
Great. Okay, so we have another question from Scott Watson, who says, great talk. Do you think enhanced meltwater intrusion down the back of the disconnections will accelerate mass loss on the lower parts and create voids? Or are there meltwater flows generally low from the upper parts?
I mean, I think most of the there's not a huge amount of superglacial meltwater because these glaciers are very temperate, so the meltwater can generally make its way to the bed and then be evacuated. Just trying to understand the question. So you're asking whether these disconnections offer an opportunity for meltwater to then access the bed of the glacier, superglacial meltwater to then access the bed of the glacier. I don't think they're associated with moulins as such. I think they're more associated with the big crevassing. So I'm not sure. Maybe we can talk about
that. I'm interested with the questions that other people are typing away. And I have to admit that I might have gotten lost just looking at the maps, and maybe you were describing it while I was just looking at all of these details in these beautiful maps. It looked to me as if a lot of these discontinuities are at a similar elevation.
Yeah.
Draining the system. Is that just happenstance? Is there a self-organizing balance between glacial dynamics and the shaping of the topographics eroding that makes the discontinuities cluster at a specific elevation?
They're occurring at the edge of this plateau. So we have this fairly low slope plateau, and then everything is very steep, and then everything's very flat again. So we have a big step in the glacier. So along the long profile, the glacier goes fairly flat, fairly steep, fairly flat, or low slope, steep slope, low slope. And this is largely controlled by geology, by topography. So, and we also have a big infilling basin of ice. So Taku Glacier is hundreds and hundreds of meters thick of ice, and that's why it's very, very flat. And I think it's the steep slope that's really key. So these disconnections are occurring in the steep slope, and that's because the ice there is thin. So if you start getting melt there, the ice then is more able to melt all the way through the glacier. Whereas on the plateau, the ice is thicker, and in the valley, the ice is thicker. So melt there doesn't expose the bed. But when you have melt somewhere where the ice is thin, it's easier for you to expose the bed.
And if we were to step back in terms of, I think I understand this relationship once the topography is established, but why didn't the ice stream cut a valley at that place? Is that a band of harder lithologies, or is there
why is there a step?
Exactly. If we think about the evolution of that system over, let's say, 500,000 years of repeated glaciation.
Yeah, the bedrock is quite, it's a lot of granite, so it's quite resistant to erosion. It's mostly fairly tough rock. I think it's a coincidence of geology and climate, because if it was slightly warmer, you would maybe have had mountain glaciation instead of this really, really thick ice mass. And there's possibly also, I mean, I haven't really thought about it from a much longer timescale, but it's also in the center of the Cordilleran ice sheet, and there may be legacies associated with that as well.
Thank you.
Well, we don't have more questions, but I have one. Regarding the disconnections, I don't know if I understood correctly from your maps. Once a disconnection is created, this is a permanent state?
It's $1 million question, Rita. I think we have a feedback system where it becomes harder for the glacier to advance over it. I suspect what we're looking at is a hysteresis in that system. If it gets cold enough and snowy enough, sure, the glacier will re-advance over that disconnection and rejoin with the ice mass below. But if we just stop warming, we have a lot of positive feedbacks that enhance melt and contribute to greater melt. So it's harder for the glacier to re-advance over it than it was for the bedrock within that glacier to be exposed in the first place. So it's a hysteresis in the system.
Concerning the first part of the presentation, at some point, if I got it right, you were speaking about changes in slope. Was that it? Have you observed different on the plateaus when you were describing the first data analysis of the 30 years, I guess? What kind of conclusions are you getting regarding the slope? Or why is the slope such an important variable for the analysis of these glaciers?
I think it's allowing us to see where we have points of vulnerability within the glacier. So where glaciers may be more susceptible, or where things may be more likely to form. Right at the start, I was talking about low slope glaciers, and that's because if I can put, if you're talking about one of the very first slides that I put up, I can share that slide again. In this picture, I've put two different kinds of glacier up. So one's a valley mountain glacier, which has got a fairly steep slope, and one's this plateau icefield, which has a fairly low slope. I was talking about the sensitivity of the glacier to a rise in the equilibrium line altitude. The equilibrium line altitude is approximately equivalent to the late summer snow line. So it's where we have net snow gain above and net melt below. If your temperature rises by a degree, and so your snow line rises up by a certain amount, if your surface slope is quite steep, then you lose less of your accumulation area. Whereas if your surface slope is quite low and you rise by that certain amount, you lose more of your accumulation area. So that's why we have sensitivity to slope. Is that the question that you were asking about?
Perfect. Thank you so much. Was that?
And I think, was there?
And there's another question as well from Cameron that, well, hi Bethan, thanks for your wisdom talk. Do you know if this ice field hypsometry is common outside the Alaska? I'm curious if you think that glacial disconnections are potentially a significant, unaccounted mechanism for increased ice volume loss on a global
Yeah, I mean, pretty much everybody I speak to who's been doing field work in other parts of the world says, oh yes, we've seen these. These happen everywhere. I was in Austria a couple of weeks ago. All of the glaciers in Austria, they all seem to have big rocks poking through the middle of them. This is happening in the Himalaya. I've mapped them in Patagonia. I've seen them in the Antarctic Peninsula. So I think these are happening everywhere where we're getting glaciers that are thinning, and particularly where we're getting glaciers that have topographic steps within them that mean that they may have points that are more vulnerable. So yeah, I think this is likely to be happening in lots and lots of different places and lots of different hypsometries. And it's something we definitely need to think about.
That's really cool. And I think that is a great way to end the talk. The mic drop moment right there. Luca, you are just unmuted. Did you have another question or?
No, I just wanted to commend some of our audience for the very good topical and strong game in the Zoom icon images. We see it's an ice community, and I very much appreciate that. So good job there, everyone.
Brilliant. Okay, well, if there are any other questions, Luca, is the Discord up and running, or?
It is always.
It
It's humming more than running, but it's humming quite nicely.
So there's a place there to ask more questions, and we can pass them on to Bethan. Yeah, I think that's it. Otherwise, next week we have Todd Elias, who's coming. I can't remember the name of his title of the talk, but next Thursday, the normal time. Hopefully see a lot of you then. Thank you very much, Bethan.
Thank you. Thank you. Bye-bye.
Bye.
Bethan, these maps are really beautiful.
Thanks. Thank you. I quite like mapping. It's very therapeutic.
Yeah, it shows.
After a long day, you can map and then you can feel that you have succeeded at something.
I understand that. Yeah.
Yeah.
Thank you very much for the presentation.
Yeah. Thank you very much, everyone. See you soon. Bye-bye.
Bye-bye.
Bye, Bethan.
All right.
Nice to see you.
Nice to see you.
Bye.